Good day, everyone. I am Reydel Joshua P. Motlog of the first group, and together with Mr. Kaleel Aggarao, Red Alray Emphasis, Loruelle Grino, Nico Jay Ledesma, Justin Pelegrino, and John Berth Pescador, we will be talking about the manufacturing of rubber. So, as we all have known, rubber has been around for almost over a century already, and it's been a very integral part towards our uh, innovation or its role in the industries over the last century has been unparalleled, and it's been a very useful material across different uh, variations of uses. And today we'll be talking about how it is manufactured. So in the late 1930s, the United States used over half of the world's natural rubber supply. And today, natural rubber can be found in over 50,000 manufactured products uh, in the in the United States alone, and the U.S. imports over 3 billion pounds of natural rubber each year. However, over 70% of those rubber used in modern manufacturing processes are synthetic rubber. So, uh, between the two kinds of rubber, the uh, natural rubber and the synthetic rubber, both of them have uh, differences that we will be talking about later on this topic. So, natural rubber begins as latex. Latex consists of the polymer called polyisoprene suspended in water. So it's a long chain of molecules composed of many individual units, of polymers connected together to form a polymer. Now, rubber is a special form of polymer called an elastomer, meaning that the polymer molecules can stretch and flex. So it's the property that stretch and flex that gives the rubber its no uh, sticky sensation. That's it. So over 2,500 plants produce latex, a milk-like sap-type material as seen in the photo, and milkweed might be the most familiar latex-producing plant to many people. But commercial latex comes from a single tropical tree, Hevea brasiliensis. Now, it originated in South Africa over 3,000 years ago. So, as the name suggests, the rubber tree originated in the tropicals of South America, and some American civilization mixed latex with morning glory juice to create rubber. So, changing the ratio to morning glory juice changed the properties of the rubber from bouncy balls to rubber sandals. The Mesoamericans knew and used rubber. So, uh, as you can see in the name Hevea brasiliensis, Brazil, which is also located in South America, is where these rubber trees originated. So, we have counts of natural advantages of natural rubber. So, first, it is inexpensive. It exhibits good abrasion resistance. It's a gold elastic mold rubber, and latex molds are good for casting wax and gypsum. So, moving to its disadvantages, we got low cost latex products generally shrink, and making molds with latex rubber is slow and time consuming, usually reaches up to 10 days. And natural rubber are not suitable for casting resins. So, let's move over to the natural rubber manufacturing, which will be discussed with my fellow groupmates.
So here's the natural rubber manufacturing process. The natural rubber manufacturing process begins with harvesting latex from rubber trees. Harvesting latex from rubber trees starts with scoring or cutting to the bark of the tree. When tappers peel back the bark of a rubber tree, they disrupt the plant ducts. This releases latex, a milky white substance. Latex flows into a cup attached to the bottom of the cut in the tree. The latex material from many trees is accumulated in large tanks. Latex is gathered from the trees by making a cut in the bark and collecting the runny sap in cups. This process is called tapping. In order to prevent the sap from solidifying, ammonia is added. Moreover, the extraction of rubber from latex uses coagulation, a process that curdles or thickens the polyisoprene into a mass. This process is accomplished by adding an acid such as formic acid to the latex. This coagulation process takes about 12 hours. Then, water is squeezed out of the coagulum of rubber using a series of rollers. The resulting thin sheets, about 1/8 inch thick, are dried over wooden racks in smokehouses. The drying process generally requires several days. An even higher quality rubber called pale creep rubber requires two coagulation steps followed by air drying. The result dark brown rubber, now called rib smoke sheet, is folded into bales for shipping to the processor. Not all rubber is smoked, however. Rubber dried using hot air rather than smoking is called an air dried sheet. This process results in a better grade of rubber. Finally, latex is pre-vulcanized. Pre-vulcanization involves chemical treatments and gentle heating at low temperatures. With further heating, the material is turned into the hardened black rubber which we are all so familiar.
Good day, everyone. I am Kaleel Aggarao, and I'm going to discuss about synthetic rubber. So, a synthetic rubber is any artificial elastomer. They are polymers synthesized from petroleum byproducts. Additionally, an elastomer is a material with a mechanical property that can undergo much more elastic deformation under stress than most materials and still return to its previous size without permanent deformation. Synthetic rubber serves as a substitute for natural rubber in many cases, especially when improved material properties are required. So, a quick history: the expanded use of motor vehicles, and particularly motor vehicle tires, starting in the 1890s, created an increased demand for rubber. In 1909, a team headed by Fritz Hoffmann, working at the Bayer Laboratory in Elberfeld, Germany, succeeded in polymerization isoprene. It is the first synthetic rubber. By 1941, during World War II, supplies of natural rubber to the US were cut as Japan occupied Southeast Asia, a huge producer of latex. By the end of the war, petroleum served as the base for synthetic rubber, as it would in the post-war years. The manufacturing process for using petroleum was more complex, but on average was also cheaper. Progress was rapid. BF Goodrich, a known tire company today, has done early work in synthesis and became the largest producer of synthetic rubber during the war. By then, production numbers skyrocketed. For creating synthetic rubber, several different types of synthetic rubber have been developed over the years, and all result from polymerization, or the linking of molecules. A process called addition polymerization strings together molecules into long chains. Another process called condensation polymerization eliminates a portion of the molecule as molecules are linked together. Examples of polymers include synthetic rubbers made from polychloroprene, a neoprene rubber, an oil and gasoline resistant rubber, and styrene and butadiene rubber, or known as SBR, used for the non-bounced rubber in tires. In a practical sense, byproducts of petroleum, like your butadiene and styrene, are mixed and refined. Then soap suds are added to make your liquid latex. They are dried and then into bits and then pressed into bales. So bales are those sheets of synthetic rubber that are pressed together, like the previous slide. The type of rubber, the most prevalent synthetic rubber today is SBR, or the styrene butadiene rubber. Others include polyisoprene, chloroprene, neutral rubber. For polyisobutylene, it is commonly used in inner tubes of tires or linings owing to its resistance to diffusion of air through the lining. We also have silicone rubber. It is generally non-reactive, stable, and resistant to extreme environments and temperatures. So, a new class of synthetic rubber is thermoplastic elastomers. They can be molded easily, unlike conventional natural vulcanized rubber, and it has a wide variety of applications. So, why synthetic rubber? Although natural rubbers have higher tensile strength, higher tear resistance, and better thermal properties, synthetic rubbers are superior to natural rubbers in two major aspects. Those are thermal stability and resistance to oils and related compounds. So another important advantage is its resistance to ozone cracking. Um, they are more resistant to oxidizing agents, for example, such as your oxygen and ozone, which can reduce the life of products like tires. Ozone cracking, the effect of ozone cracking is the like bits and pieces of your rubber from your tires are slowly peeling off. It is induced by your ozone and oxygen. So price differential is not too high, but natural rubbers demand a huge plantation of latex producing trees. Synthetic rubbers, on the other hand, can be manufactured in bigger quantities at a faster rate as its raw materials are readily available. For the uses of synthetic rubber, the transport industry is the largest user of rubber for the production of tires, door, and window profiles. In the industry, rubber is used in we have your conveyor belts, elevator belts, hoses, rather, tubes, seismic bearings, and most importantly, the seals like O-rings, gaskets. They can also be used for mattings and floorings. And they can also be used in the industries which produce consumer goods like good footwear, erasers, sports, and the like.
And now we will discuss the processes involved in manufacturing synthetic rubber. Natural rubber changes with temperature, becoming brittle with cold and sticky or gooey when heated. Chemicals added during compounding reacts with the rubber during the vulcanizing process to stabilize the rubber polymers. Compounding adds chemicals and other additives to customize the rubber for a specific use. For example, tires. The additives will increase the tire's traction and improve wear. Additional additives may include reinforcing fillers to enhance the properties of the rubber or non-reinforcing fillers to extend the rubber, which reduces cost. The kind of filler used depends on the final product. Depending on the planned use of rubber, different filler types could be used. This includes carbon black, clay, silica, calcium carbonate, and other miscellaneous fillers such as tack, mica powder, titanium dioxide, and calcium sulfate. Carbon black is the most commonly used reinforcing filler. It is derived from soot. Carbon black increases rubber's tensile strength and resistance to abrasion and tearing. Carbon black also improves rubber's resistance to ultraviolet degradation. Most rubber products are black because of this carbon black filler. Kaolinite is a clay mineral which is an important industrial material. It is used as a reinforcing additive in rubber production. Adding clays to rubber provides semi-reinforcement which increases the modulus and tensile strength. It also improves electrical resistance of the rubber compound and lessens its abrasion. Silica is a cheap heat-resistant filler for rubber compound. These additives makes the surface of the rubber to be less hydrophilic and more rubberphilic, meaning the rubber surface will become much easier to bond with other rubber surface when treated with heat or incorporated with filler elastomer. Also, calcium carbonate. It is used as a cheap filler, which also increases the rubber's resilience and load limit. And the other fillers, we have tack, which is used for anti-stick application. Mica powder acts as a laminar filler, provides heat resistance and low gas permeability. Titanium dioxide is used as whitening agent for rubber compounds. And lastly, barium sulfate provides acid resistance and increases density of the rubber, which this can be applied when you want your rubber to be heavier. Now for the mixing process. The additives must be thoroughly mixed into the rubber. The high viscosity of the rubber makes mixing difficult to accomplish without raising the temperature of the rubber high enough to cause vulcanization. To prevent premature vulcanization, the mixing usually takes place in two stages. During the first stage, additives like carbon black are mixed into the rubber. The mixture is referred to as a master batch. Once the rubber is cooled, the chemical for vulcanizations are added and mixed into the rubber. Additives are mixed with the rubber using rubber mixing mill, where the rubber and the additives passes through in between two rollers for several times until they completely mix with each other.
Everyone. Good day, sir. My name is Red RL Emphasis, and I'm assigned to discuss about manufacturing of rubber. I'm assigned to shaping and vulcanization. Shaping. Shaping rubber products occurs using four general techniques: extrusion, uh, calendering, coating or molding, and casting. And those selected techniques will be discussed in the later parts. More than one shaping technique may be used depending on the final product. Extrusion. Extrusion consists of forcing highly plastic rubber through a series of screw extruders. As you can see at given pictures, gonna force a rubber to form a tube-like example sa picture. Uh, Calendering pro- passes the rubber through a series of increasingly smaller gaps between rollers. The roller die process combines extrusion and calendering, producing a better product than either individual process. Next, calendering. Coating uses the calendering process to apply a coat of rubber or to force rubber into fabric or another material. Tires, waterproof cloth, tents, and raincoats, conveyor belts, as well as inflatable rafts are made by coating materials with rubber. Rubber products like shoe soles and heels, gaskets, seals, suction cups, and bottle stops are cast using molds. Molding is also a step in making tires. The three primary methods of molding rubber are compression molding, used in making tires among other products, transfer molding, and injection molding. Vulcanization of rubber occurs during the molding process rather than as separate step. Vulcanization. Vulcanization completes the rubber production process. Vulcanization creates the cross connections between the polymers of rubber, and the process varies depending on the requirements of the final rubber product. Fewer cross connections between the rubber polymers create a softer, more malleable rubber. Increasing the number of cross connections decreases the elasticity of rubber, resulting in harder rubber without resulting in hard rubber. Without vulcanization, rubber would remain sticky when hot and brittle when cold, and it would rot much more quickly. Vulcanization, originally discovered in 1839 by Charles Goodyear. Uh, as you can see, there is kanang this is there is a brand called Goodyear tires. So yeah, link po siya uh, sa pag-discover sa vulcanization, no? Si Charles Goodyear required adding sulfur to rubber and heating the mixture to 280 Fahrenheit for about 5 hours. Modern vulcanization in general uses smaller amounts of sulfur combined with other chemicals to reduce the heating time to 15 to 20 minutes. Alternative vulcanization techniques have been developed that don't use sulfur. And that is all. Thank you.
Now, we will discuss the four most common rubber manufacturing processes. There are several manufacturing processes available to produce rubber products. Each manufacturing process has particular advantages that makes it an excellent choice for producing a certain type of product. Understanding the product process helps us understand the cost implications and its trade-offs. One of the most common manufacturing processes is extrusion. Extrusion begins with an unvulcanized compound being fed into an extruder. Once it's inside the extruder, it gets forced through a shape die specified by the manufacturers to have the rubber shape into the desired form. Then, the extruded product will need to be vulcanized prior to being defined as usable. It is important to note that during the vulcanization process, the rubber may swell or shrink, and the length of the extruded rubber may be impacted as well. Extrusion manufacturing has the advantage of being able to produce products in high volumes at a lower production cost. Some of the common rubber products produced from extrusion includes profiles, cords, tubings, and gaskets. Another rubber manufacturing process is called latex dipping. Latex dipping occurs when thin-walled molds are immersed into latex compounds and then slowly withdrawn. Mainly, gloves, balloons, condoms, and masks are manufactured by the latex dipping process. The thickness of the dip product can easily be increased by simply redipping the product in the latex compound. After the dipping process occurs, the product is finished by vulcanization. The main advantage of dip molding includes being able to dip latex products with even thinner walls and create more complex shapes than the extrusion method.
Hi everyone, I am Nico Jay Ledesma from ME4A and I will discuss to you my part. So, I molding it is composed of three main manufacturing processes. It is composed of compression molding, transfer molding, and injection molding. So, in compression molding, um, it is the oldest and the least expensive methods of the three, and it has a low heating time, and that's why it is time consuming and low production rate. So the next is the transfer molding. So the transfer molding fill the gaps of the um, compression molding. So it is the development of the compression molding. So it is called the transfer molding. So in transfer molding, it has a lot of um, production rate, and though it is expensive and more complicated. So next is the injection molding. So it is the third of the most common molding processes. So it has separated entities and separated controls. So, and the good thing of inject injection molding is that it can be automated. So the process can be automated. The next is the calendaring. It is one of the most common manufacturing processes. So it works by forcing softened material into the center of counter rotating rollers. So it is best in producing sheets and films of rubbers. So it has a very good benefits, especially in terms of thickness, and it is adaptive in such a way that it can produces thinner parts and wider than with extrusions. But the only thing here is it has a high operating cost. So there are a lot of manufacturing processes. It has a lot of pros and cons, and it depends with the manufacturer on what they are good with and what they are favor with.